Okay, so today we are covering Chapter 8. Okay, and the primary focus of Chapter 8 is hypothesis testing. Okay, and hypothesis testing is another method for statistical inference. Okay, and so whenever we're talking about statistical inference, we're trying to make conclusions about the population based on limited data. All right, and this time with hypothesis testing, we begin with kind of a belief or a hypothesis, a testable hypothesis. Maybe we have a question of some kind. We turn this into a testable hypothesis. Okay. So, okay, we begin with a testable. I don't know if that's a real word, but a hypothesis that we can test. Okay, and what we mean by that is it's kind of a belief. And it's a belief that can be disproven, okay? So it's a very specific notion. And when we say testable, we mean it can be disproven, okay? So, can be disproven or at least contradicted, okay? Okay, and then so we start with that, and then and the big picture is in hypothesis testing. We say, okay, well, let's just assume that this hypothesis or this belief is true. Okay, so the hypothesis is kind of like a a belief. We can see that. Okay. A belief. Okay, and then we just say, let's assume that this belief is true. Okay, and if this belief were to be true, what would the world look like? Okay, that's kind of what we say. We say if this belief were true, what would we expect the world, or in our case, what would we expect our data to look like? Okay. And then, and so this, what we expect the world to look like, this we can say is kind of our expectation, okay? And then we look at the data, and the data will be what the world actually looks like, okay? Okay, and so this we can call the reality. Okay. And so we compare our expectation versus the reality, right? And this is where we do the testing, okay? The testing is really, we compare the expectation versus the reality, okay? And if the reality, if the data matches very closely to our expectations, then we have no reason to doubt our set of beliefs, okay? Okay. On the other hand, if there is a huge difference between the reality and the expectation, sorry, let me just get my slide set up. If there is a big difference between the reality and the expectation, then we have reason to doubt our beliefs. Okay, our belief being the hypothesis. Okay, does this kind of framework make sense? So we say, all right, I'm going to start off with the assumption that so-and-so, this new person I met, this person is a good guy, okay? And then we go about and we start off with that assumption, and then we just see what the data says, right? Okay, and if if we observe this person that we meet, this person helps people and is nice and all of these things, we have no reason at this point to doubt our belief that this person's a good guy, this person is trustworthy or something. Okay, all right. On the other hand, maybe we meet someone else and we also start off with the initial belief, this person is a good guy, this person's a trustworthy person, okay? But then as time goes on, we observe this person and we see this person lie, cheat, or steal, or do things like that. Then we say, well, if this person were a good person, my expectation of his behavior is not lining up with the reality of the behavior, okay? And because there is a difference between how I expect a good, quote, good person to behave and how I'm seeing this person behave, because there's a difference there, now I have reason to believe or reason to doubt my initial belief about this person, right? And so we are just, in statistics, we're going to start off with kind of this initial belief, right? And it's going to be, a little bit more boring with numbers and whatnot. But we're going to say, if this were true, then we expect our data to look a certain way, okay? And if the data ends up looking similar, okay, maybe it's not going to look exactly like it, but if it looks pretty similar to how we expect, then we have no reason to doubt that, okay? On the other hand, if the data that we observe is quite different, then we have reason to doubt these beliefs, okay? So then there's this question of how do we know when our reality matches closely with the expectation versus how do we know when there's a, quote, big difference between the reality and the expectation, right? And this part, deciding when there is this little difference or a big difference between the reality of our data and what we're expecting, that's where our understanding of sampling distributions and probability comes in, okay? But I just kind of want to make sure, from a high-level perspective, this idea feels okay. Okay, so how will we know if the reality, okay, we'll call our reality the observed data, and the expectation, are similar or are similar or very different. Okay. And so what we're going to do is basically all of these things, we're going to have, the kind of values assigned to them. But we're going to compare the difference. We're going to be able to measure the actual difference between the data and the expectation, okay? And we will compare that difference, and we're going to divide that by the standard error. And we're going to see how many standard errors are we different, okay? So we're going to get something called a test statistic. And the test statistic is basically the difference between the observed minus the expected. Okay, we're going to take the difference. This is the difference between observed and expected. Okay, and we're going to take that difference and we're going to compare it, or we're going to divide it by the standard error. Okay, and what is the definition of the standard error? You guys remember? Standard error is the standard deviation of what? The sampling distribution. Okay. Does that sound familiar? Yeah, I hope. Okay, what's the sampling distribution again? That's the standard error. The standard error is the standard deviation of the sampling distribution. And what's the sampling distribution? This is what we talked about last week. It's the distribution of all possible sample statistic values, right, for a given population. If we're talking about proportions, it's the distribution of all the different possible p-hat values we can get, okay? Yeah. Everything kind of builds on each other, right? Okay. All right, and so this is going to give us an idea, and what we're going to do is we're going to say what is the probability of getting this test statistic, okay? And this probability is called the p-value. What is the probability? This thing is, or what is the probability of getting this test statistic? The value here is the p-value, okay? The answer to this question is the p-value. It's called All right, so I'm just kind of throwing all these definitions and terms out here, all right? And it's going to feel a little bit wonky in the beginning, but we'll do some practice, and I hope it will start to make sense once we see it in a kind of a practical context, okay? And so I'm going to put the formal definition of the p-value up on the screen. This is a good definition to learn. The p-value is the probability of observing our data or something more extreme if we assume that the null hypothesis is true. Okay, and I know I haven't told you what the null hypothesis is yet. That's okay. We're going to just put this here. And so the key thing here is that the p-value is the probability of seeing our data. It's the probability of observing our data. That's the key part. And it's kind of if we assume that the null hypothesis is true. All right. So, and it's the same thing. You know, what's the probability of getting this test statistic? That's also the same thing. The p-value is the probability of observing our data or something more extreme if we assume that the null hypothesis is true. This is what we're talking about here. Okay? And if it turns out that we are likely to get our data, okay, what's the probability of observing our data if the null hypothesis were true? If the data we get is very probable if under the null hypothesis, or assuming that the null hypothesis is true, if the data is very probable, then we have no reason to doubt our belief, our null hypothesis. Okay? On the other hand, if it's incredibly unlikely to get our data if the null hypothesis were true, and yet we have this data, then that means our belief, our null hypothesis, is probably wrong. Okay? So I'll write that up on the next screen, and we're going to keep. So, okay. If it is likely to observe our data okay, if when the null hypothesis is true, okay, then you know, then our data does not cast doubt on the belief, or I'll say on the null hypothesis, which is our belief. Okay. On the other hand, if it is unlikely observe our data when the null hypothesis is true, okay, the fact that we observed this data then casts doubt on the null hypothesis. Which is our belief. Okay, so I'll let you guys get that written down, and then I'll kind of give you an example. All right, we good? Okay, so let's say you play a game with a friend. Okay, it's a very simple game. Okay, basically, you just flip a coin. Okay, and then, you've picked one side, and so, if it lands heads, you win. Okay, tails, your friend wins. Okay, and so, all right, so let's say you play, so scenario 1. Okay? Basically, for whatever reason, your friend ends up doing all the flipping, okay? Your friend, okay, does all the flipping. Okay? And you play 10 games. And the results is it lands tails 7 times. Okay, so your friend wins 7 and you win 3. Okay, tails 7 times. All right. Okay, so let's talk about this. Okay. We're going to start off with the initial belief, okay, which we call the null hypothesis. Okay? And the null hypothesis in this case is that our friend flipping the coin is not cheating, is doing this fairly, okay? Our friend is playing fairly. Okay. Is that all right? Okay. If this belief were true, what would we expect the game results to be? We would expect the friend to win 5 and we would win 5, right? That's what we would expect. Okay? So if this belief is true, we expect to win 50% of the games. Okay? What is the reality? We win only 30% of the games, okay? So if this belief is true, so results tail 7 times, we win only 3. Okay, so the reality is we won only 30% of the games. Okay. At this point, You've played 10 games and you've only won 3 of them. Would you accuse your friend of cheating? Would you accuse your friend and say, I think you've done something to the coin to give yourself an advantage or to disadvantage my probability of winning? No. Probably not, right? I mean, we could just say, oh, bad luck, right? When you flip the coin 10 times, it's very possible that you only win, that you only get 3 heads, right? So, you know, when we look at this, the difference between the expectation and the reality, there's a 20 percentage point difference, and we'll have to talk about the standard error here. But basically, at this point, you know, we would not accuse our friend of cheating. Is there one C? Okay. Accuse our friend of cheating. Is it possible that he's cheating? And that's why he won 7 games out of 10? It's possible, okay? But right now, after playing 10 games, we don't really have evidence either way, right? We don't have evidence. We wouldn't say that winning, the fact that we've only won 3 games means he's somehow disadvantaging us, okay? It just means maybe we just got unlucky, or maybe our friend is doing something shady, okay? We don't know, right? So we would not accuse our friend of cheating, okay? From probability, okay, there is a fairly decent probability that, you know, a fair coin tossed 3 times, I'm sorry, tossed 10 times, ends up with only 3 heads. Okay, or in other words, it is quite possible to get the data we have even when our null hypothesis is true. I'll put that in. So it is quite possible to get our data even it's true. Do we agree here? Do you remember what the p-value is? P-value is the probability of getting our data if we assume the null hypothesis is true. Okay? So if we say it's quite possible to get our data even when the null hypothesis is true, does that mean our p-value is big or our p-value is small? What do you guys think? P-value big, p-value small in this situation here? In our case, the p-value is large. Okay? So I just want us to imagine this scenario, right? We've played 10 games, you only won 3, okay? You're expecting to win around 5, okay? But you only won 3 games. Is the difference between what you expected and the reality, is that a big difference or is it a small difference? And in this case, we're saying it's kind of a small difference. And if I look at my data and I ask, what's the probability that I would get only 3 wins out of 10, even when we're playing fairly, we would say, well, it could happen, right? It's fairly likely to happen. And we could actually do these calculations. Okay, we would look in the binomial table and we'd say, what's the probability of getting only 3 out of 10 with a n is 10, x is 3, and p is 0.5. And because we're looking at the data or something more extreme, we would also look at the probability of getting x equal to 2 and x equal to 1 and x equal to 0. And those things get smaller and smaller. But we would add all of those together and we'd say, oh, well, there's a decent chance that this could happen. Maybe about 1 in 6 chance. Yeah?
But the thing is that it says only 3 heads or fewer. I mean, 3 heads, yeah. But wouldn't you say like 2 heads or 1 head? If in the long run, the average would be you would get 5 heads.
Yeah, but we just played it one time.
Right.
We just played it one time, okay? I mean, we just played one session of 10 games, okay? And in that case, it's quite possible that you just got bad luck and you won only 3 of the games, okay? All right, on the other hand, let's try scenario 2. For whatever reason, you let your friend do all the flipping. Okay, your friend flips the coin 1,000 times. Okay, and you win only 300 times. Okay, do you think your friend is cheating now? Yes, no, maybe? So you're, huh?
I'm suspicious.
Yeah, now we're suspecting something fishy is going on, right? You're saying, okay. So again, under our initial belief, our null hypothesis, which is friend plays fairly. Okay, or we can express this null hypothesis symbolically. We would write H0 to indicate the null hypothesis, and friend plays fairly, we would say P is equal to 0.5, P being the probability that we win. Okay, and we say if P is equal to 0.5, if the null hypothesis were true, okay, we expect to win about 50% of the games. Okay, the reality is we only won 30%. So this time P hat is equal to 0.3, okay? And this time, the big difference here is that we've played 1,000 games now, okay? And so we can ask, well, what is the probability? If we play 1,000 games, is it possible that from random chance, like if I were to flip a coin 1,000 times, is it possible that it lands heads only 300 times out of 1,000? It is possible, but we can say, how likely is that to happen? Okay, and we can do the math, and it turns out that it's incredibly unlikely. Incredibly unlikely. You're more likely to hit Powerball 2 weeks in a row, okay, picking random numbers, okay? And we can say, well, maybe our friend just got that lucky, okay? But that's probably not what happened, right? Okay, we would have reason. We would say, I don't know what happened, but I think something fishy is going on. Okay, so the reality is we won only 30% of the games, okay, we can do the calculations, okay? We can do the calculations and say, and ask, you know, if we flipped a fair coin 1,000 times, what is the probability that it will land heads only 300 times? 300 times or fewer. Okay? And the answer is, it is possible, but it's very, very, very unlikely. Technically possible. Incredibly unlikely. Okay? And so the fact that we observed a series of 1,000 coin flips and it landed heads only 300 times indicates to us that something is going on where this is actually not a fair coin. Okay, and so in this case we have the p-value is small. Okay. I don't know why All right, so let's try an actual scenario here. Okay, and we can and so and these were kind of extreme cases where you played 10 games and you won 3 versus you played 1,000 games and you won 300. At what point do we what if you play 100 games and you win only 30? Is that going to cast doubt? What about 50 games and you win only 21 or something like that? We can think of different scenarios and we can say, well, at what point do we say this is different from reality? Okay, so we'll set up a framework and we'll try this out. Okay, so we'll say hypothesis testing in 4 steps. Okay, so we start off with step 1, and this is writing our hypotheses. Okay, so hypothesis testing. We'll say in 4. Okay, so write our hypotheses. So when we write our hypotheses, we have a null hypothesis. Okay, which we write as H0, okay? And for our initial kind of hypothesis tests, we will do hypothesis tests for proportions, and we're going to start off with just seeing 1 sample at a time. Later in today's class, we'll look at 2 samples at the same time. But for the initial one, we're going to start off with P is equal to some number, maybe like 0.42. This is just an example, okay? So basically this says the null hypothesis says, you know, we believe that the proportion of whatever, that the proportion in the population is 0.42. Okay, so maybe what proportion of people I don't know, have a pet or something, okay? Maybe 42%, I don't know. We're just making stuff up here, okay? So key things is that the null hypothesis will always have an equal sign. And that's what makes it testable, okay? Because we can have data that contradicts that p equals 0.42. If you have something, if the null didn't have an equal sign, then it makes it difficult to test, okay? So the null hypothesis is p is equal to some number, okay? Or, you know, generically, the generic null hypothesis would be p is equal to p0, p0 being some number like 0.42, okay? And then we have the alternative hypothesis. Okay, and the alternative hypothesis is identical to the null hypothesis, except we replace the equal sign with either a not equal sign, a greater than sign, or a less than sign, okay? And here I'm going to introduce some terms here that we'll talk about later, okay? If the alternative has a not equal sign, then it is a two-sided test. Okay, and if otherwise it's a one-sided test. If the alternative has a greater than or a less than, then it is a one-sided test. So we say p is equal to 0.42 versus the alternative that p is not equal to 0.42. Or, you know, p is equal to p0 versus the alternative that p is not equal to p0, or p is greater than p0, or p is less than p0. Okay, step 2, this is called the preparations. Okay, so technically we're supposed to check the conditions to use the central limit theorem. Because most of our tests depend on the use of this central limit theorem. So what are those conditions again? We have 3 of them. we have the independent and random condition. What else do we have? The large sample condition, meaning our sample has to be big enough. And lastly, the big population condition, okay? Now, when it comes to exams, it's difficult to incorporate this step into the exam, okay, without it feeling like I'm setting you up for a trap, okay? Because, you know, it's one thing to kind of write out a problem and say, okay, do the test, and then say, oh, just kidding, the conditions weren't met, so you weren't supposed to do the test. And it feels a little trap-like. So, so during the exam, it'll be kind of set up like the today's quiz, in that I'll have a section where you're just checking the conditions, okay? And you decide whether or not the conditions are met. And then when it comes to doing actual hypothesis tests, and all of those tests, the conditions will be met in order to continue on, okay? So I've kind of separated it out so that when you do the actual test, you don't have to worry about checking the conditions because they'll be met, and you can focus on doing the actual test. Okay? There is also another part of the preparations, which will be identify the significance level. And I'll get into this later. The significance level, this is called alpha. The symbol looks something like that, okay? Identify the significance level alpha, and the test will either say, you know, the problem will say, use a significance level of this, okay? And if it doesn't say that, then assume alpha is 0.05, okay? Alpha is not given in the problem. Okay, assume alpha is 0.05. And this is the line at which we say it's, and basically the significance level is, it's kind of an arbitrary line at which point we say the p-value is big and the p-value is small, okay? This is, okay. All right. Oh, go back? Yes, I'll go back.
Does that mean 0.06 is a big p-value?
Yeah, it feels a little arbitrary, but if your p-value ends up 0.06 and you're using alpha as 0.05, then you say my p-value is big, and everything that goes with that, okay? It's kind of just like in the United States, 18 is the magic number for when you are an adult, okay? And so as soon as you turn 18, you can open up credit cards and get yourself into thousands of dollars of debt. You can, you know, sign college loans, you know, hundreds of thousands of dollars, and you're responsible for them because, you know, but at 17, you know, you're kind of shielded from a lot of these mistakes. So, yeah. Are you responsible for all your actions once you're 18? Pretty much. But yeah, so 0.06, yeah, that's considered, quote, big. 0.04, it's considered small. And it's a little bit arbitrary, but that's what happens when you draw an arbitrary line, okay? And so, you know, lately it's been coming under a lot of fire, this p-values and things like that. They're saying like, well, since when did 5 become the magic number and things like that? And I think there's a lot of valid criticisms to that, but this is kind of the classical approach to hypothesis testing, and it's kind of become accepted, right? And 5% is probably a good value, but anytime you have a strict line, you get these slightly weird situations. So yeah, so yeah, you'll there's a lot of yeah, I don't know, just you'll see research papers published with p-values of like 0.049 or 0.048, where it's like, oh, you just barely made it. And then you kind of feel like, well, you know, did the researcher do any kind of fudging of the numbers? There's something called p-hacking, which is basically like the researcher inadvertently made some subconscious decisions that kind of artificially skew the thing so that it you end up getting p-values just under 0.04 and things like 0.05 and things like that. Maybe, you know, okay, so here's an example where stuff like this happens in real life, but in a completely different context, right? So, you know, for your Social Security benefits to kick in, you have to be like 62 or 65 if you want the full thing. And so what this has caused, the inadvertent side effect of this, is that as soon as people turn 65, they retire, right? It's very rare these days to find some people continuing to work after age 65, because there's kind of this almost automatic expectation that as soon as you hit 65, you're gonna retire. And, you know, it's probably a good point to have people retire around that age, but there are certainly, you know, and it's different from person to person, but there are certain people that are probably, you know, still have many more productive years in them. Maybe not many, but still have some productive years in them. But because, you know, we've legally said this kind of this monetary reward to say that, like, oh, at 65, you're gonna get the, you know, that's the best that what's gonna happen, you know, retire. And so should people automatically retire at 65? Maybe, maybe not, I don't know, but that's just what happens. You don't find a whole lot of people sticking around working much longer than that. I mean, of course there are, but there's kind of like an automatic expectation there. So I don't know. And so, you know, as far as research goes, you do find a lot of papers published with p-values right around 0.05, you know, just barely under it. And because of that, people have questioned whether that's good or bad. Let's see, hang on a second. Okay, step 3 are calculations. Okay, and these calculations are specific to hypothesis tests for P with one sample. Okay, and we're going to break this down into 3 parts. Part 3A will be find the standard error. So you have standard error equal to the square root of p0 times 1 minus p0 divided by n. Okay, what's p0? P0 is the value, is the number that appears in the null hypothesis. So in this case, it's, 0.42. Okay, so once you have your standard error, then you'll find your test statistic. And the test statistic is the difference between the observed versus the expected divided by the standard error. Okay, and so in this case, we're going to get a z-score, and we're going to say our test statistic is z, and the observed value is p-hat, our sample proportion. If the null hypothesis were true, we would expect our p-hat values to be close to p0. And we would divide that difference by the standard error. So we're taking the difference between what we observed, between what we expected, okay, or the reality versus the expectation, and we're going to take that difference and divide that by the standard error to see, is it a big difference or not, okay? And then lastly, we're going to look up the test statistic to get the p-value. And I'm going to have to explain that more on the next page. Okay, so let's, can I flip to the next slide here? Okay, so getting your p-value. Getting your p-value from a z-score. Okay, so we're going to start off for one-tail scenarios, okay? So if the alternative has a less than sign, then the p-value is the area to the left of the z-score. Okay, so basically you're going to just look up the value in the table, and that will be your p-value, okay? Because the table always gives you the area to the left, okay? So. Okay, if the alternative has a greater than, then the p-value is the area to the right of the z-score. So in that case, look up z in the table and subtract that from the from 1. All right, and then we have two-tail scenario, two-tail test. So this is if the alternative has a not equal sign, then the p-value is 2 times the tail area. Okay, so the tail area is the area to the left of negative z and the tail, or the tail area is the area to the right of a positive z. Okay, so you're going to look up the tail area, either area to the left of negative z or area to the right of a positive z, and then you multiply that by 2 to get your p-value if you have a two-tailed test. And that's if the alternative has a not equal sign. Is that all right? Okay, and then, all right, and then the last step, step 4. It feels like a lot. You do it a few times, you'll get the hang of it, okay? All right, step 4 is make a conclusion. Based on the p-value. Okay, so basically, compare the p-value to alpha. Okay, so if the p-value is bigger than alpha, then that means the p-value is, quote, big. The p-value is large. So what this means is we do not have evidence to reject the null hypothesis. Okay. Another way of saying this is that even if the null hypothesis were true, or even when the null hypothesis is true, you know, there is a large, or at least a non-negligible probability of observing our data from random chance alone. Okay. Or if the p-value is less than alpha, okay, then the p-value is small. Okay, and then we would say we have evidence to reject the null hypothesis. And that means, you know, if the null hypothesis were true, okay, then it is very unlikely to observe our data as a result of random chance. Okay, so the fact that we did observe our data causes us to believe that the null hypothesis is wrong. why don't we take a short break here? We'll say 10 minutes, and then we'll work through some examples, and then we'll add on to all of this.